morning, everybody. We shall start from where we left the other day. The theme is still composition and systematic classification of minerals. We saw yesterday in the previous lesson three aspects of this lesson. In elements and minerals, it was shown that minerals could be a single element or a group of them, and that mineral formation is a very systematic process. We also saw that the bulk of the minerals of the earth crust are made up of just 8 elements called the major elements: oxygen, silicon, aluminum, iron, magnesium, calcium, sodium and potassium. Minor and trace elements find their way into other common minerals by substituting for major elements. Ore minerals, extremely rich in a number of minor and trace elements, are a rarity and need special conditions and processes. In chemical composition and mineral formulas, we noted that formulas speak of a mineral composition in a nutshell. It could be as simple as Au for gold or much complex for minerals like tourmaline. Number of formulas like empirical and structural, general formula, atomic variations, solid solutions, variable formulas and formulas for hydrous and hydroxide minerals were commented upon. Finally, Berzelius' system of mineral classification was dealt with, which is based upon the nature of anionic group present. Thus, mineral kingdom was divided into native elements, sulfides, sulfosalts, halides, oxides and oxygen salts, which includes carbonates, borates, sulfates, phosphates, chromates, arsenates, vanadates, tungstates, molybdates, urinates and tellurides. Though the most widespread and important group, the silicates also come under oxygen salts. They deserve a separate and special treatment. In module 4, we shall deal with silicate and non-silicate minerals. Silicate minerals are the most dominant members of the vast mineral kingdom. As a group, they are unique and deserve special mention for two reasons. Firstly, in the earth's crust, they are the most important and abundant group of minerals. If we include silica group as silicates, they make up 95% of the earth's crust. Secondly, there is tremendous diversity to their atomic structure, making study of silicate structure a celebrated topic of undergraduate mineralogy. They are all derived from a basic tetrahedral unit, SiO4. Other cations like Al, Mg, Fe, Ca, Na, K are also important, but the fundamental unit around which other cations come and participate in mineral formation is SiO4. Here Si is at the center of the 4 oxygens or at the corners of a tetrahedron. This coupling between Si and O therefore becomes one of the most strongest bonds in the mineral kingdom. The vastness of silicate group of minerals arises from the fact that there are many ways in which different SiO4 are related to each other. They could be independent or exhibit a large number of sharing arrangements of common oxygen anions. Depending upon these various arrangements, they have been given different names, which are nesosilicates, sorosilicates, cyclosilicates, inosilicates, phyllosilicates and finally tectosilicates. Diversity of silicate structure in nature is attributed to the unique behavior of the element silicon and results from its dual capacity to behave like a true metal, non-metal, or anything in between. In quartz, for example, it behaves like a metal, that is a SiO4, combining with anion oxygen, whereas as a SiO4 unit, say, in the structure of olivine, it behaves like an anion group. Silicate minerals in various proportions constitute silicate rocks that make bulk of the earth's crust. These are of four types: acidic with abundant silica with little iron and magnesium, intermediate falling between acidic and mafic which are abundant iron and magnesium and relatively less silica, and ultramafic, very little silica and abundant iron and magnesium. Coming to non-silicate minerals, bulk of the earth crust, no doubt minerals are fairly common and exhibit a large variety: metals, semi-metals, non-metals, sulfides and sulfur salts, halides, oxides, oxygen salts, which includes nitrates, carbonates, sulfates, chromates, molybdates, tungstates, phosphates, arsenates, vanadates and borates, to name a few, are the important ones from a much longer list. Of these, the most abundant are quartz, hematite, magnetite, corundum, ilmenite, pyrolusite, chromite, which are all oxides, followed by calcite, dolomite, magnesite, siderite, all carbonate, barite, gypsum, which are sulfates, and apatite, monazite, which are phosphates, fluorite, halite, which are haloids, pyrite, chalcopyrite, sphalerite, chalcocite, galena, pyrrhotite, all sulfides, and gold, silver, platinum, sulfur, diamond, and graphite, which are all native elements, and finally bauxite, which is a secondary mineral. In module 5, the title is The Occurrence of Minerals. Classification of minerals and their general occurrences needs to be grasped together at an early stage. Some may like to classify minerals genetically, for instance, minerals formed by different geological processes like magmatic, volcanic, scan, hydrothermal, sedimentary or metamorphic. Rocks are the storehouses for minerals. Most of the rocks contain a group of minerals. Rarely is a rock composed of a single mineral like in quartzite, a metamorphic rock consisting essentially of mineral quartz only. Thus, to learn about formation and occurrence of minerals, we have to learn about the rocks that contain them. There are three great categories of rocks, namely igneous, sedimentary and metamorphic. These are further divided into plutonic, hyperbasal and volcanic. Sedimentary rocks could be of mechanical, chemical or biochemical origin, while depending upon the pressure, temperature conditions of metamorphism, we may get different types of metamorphic rocks. According to an old estimate by Clark and Washington given in 1924, the upper 13 kilometer of the earth crust has the following proportion of rocks: 95% igneous and metamorphic, and 5% sedimentary, out of which 4% shale, 0.75 sandstone and 0.25 limestone. There may be quite an overlap so far as occurrence of a particular mineral in the three categories of different rocks of the same category is concerned. However, the occurrence is not a haphazard process. certain minerals are more common in a particular rock or rock association. Olivine, for example, will be hardly found in an acid igneous rock like granite, or the mineral zircon will hardly be found in basalt. Then there are certain minerals which are more characteristic of a particular category of or type of rock. Garnets and chlorite are typical of metamorphic rocks called schists. Calcite of marble, kyanite too is a typical metamorphic mineral. The mineral quartz, in a sense, is ubiquitous, that is omnipresent, making its appearance in all three categories of rocks, but not all igneous rocks will have free quartz. Now we shall deal with common minerals of the igneous rocks. Among silica minerals, quartz is the most dominant. In acid rocks, potash feldspars, that is orthoclase and microcline, and among piezochemical cases, albite and anorthite are most common. In basic rocks, labradorite is dominant. Nepheline and sodalite are the main feldspathoids to be found in undersaturated rocks. Olivine is common in basic and ultrabasic rocks. Ancestite, diopside, augite are common igneous pyroxenes, while aegirine is frequent in alkali rocks. Among amphiboles, hornblende, anthophyllite, tremolite and alkali amphiboles are common, and biotite and muscovite both are usual members of acid to intermediate rocks. Minerals that occur in small amounts such that they do not affect rock classification and nomenclature are termed accessory minerals. Apatite, zircon, magnetite, sphene, rutile and tourmaline, which is a complex hydrated silicate with fluorine, are among the most important accessory minerals recorded in igneous rocks of plutonic type. Now coming to common sedimentary minerals, we will see that very large numbers of minerals have been recorded from sedimentary rocks. The reason is obvious. Any older rock formation, whether igneous, metamorphic or even an older sedimentary rock, can be subjected to the process of weathering, leading to sedimentary and ultimately to sedimentary rocks. However, common and abundant minerals of sedimentary rocks are fairly limited, belonging either to the resistant mineral group or the newly formed mineral group. Of the first category, the mineral quartz again heads the list. Feldspars are less common. Some of the less common accessory minerals, by virtue of their hardness, are also found as resistant minerals, including zircon, rutile, magnetite, ilmenite, monazite and cassiterite. Precious metals, gold, platinum and gem minerals like diamond and others are also included in the list. Among the newly formed minerals, by a combination of processes of mechanical, chemical, biochemical and biological nature, the list is quite large, but the dominant minerals groups include calcite, dolomite, few silica minerals, clay minerals, mostly kaolinite and montmorillonite group, illite, chlorite, limonite including goethite, hematite, gluconite, bauxite including gibbsite, bohemite, colophane, sedimentary apatite and typically evapotite minerals, gypsum, anhydrite, calcite and halite are important. Common minerals of the metamorphic rocks, we shall see that mineralogy of the metamorphic rocks can be extremely diverse, since any kind of earlier rocks can be subjected to metamorphic process which can take place over a wide range of temperature and pressure. Yet the list of commonest metamorphic minerals is not very large, as a large number of them have a wide stability field. Following are the more common metamorphic minerals in four of the most common metamorphic rock groups, namely schists, gneisses, granulites and marbles. Among silica minerals, quartz is the most abundant and common in silica-rich rocks. Under high temperature and low pressure, tridymite and cristobalite may appear. Among feldspars, microcline is the commonest variety, while albite is the commonest plagioclase. Less so is anorthite. Calc aluminium silicates, zoisite and epidote are fairly common. Pyroxenes including diopside, enstatite and are common, while jadeite is a typical metamorphic mineral. Among amphiboles, hornblende is common, while anthophyllite, cummingtonite and tremolite are very characteristic. Actinolite and glucophane are also very common. Garnets are the most typical members of the metamorphic rocks. Common varieties include pyrope garnet, almandine garnet, which is iron aluminum garnet, and grossularite, which is calcium aluminum garnet. Micas, serpentine, talc, chlorites and chloritoids are very common, as also muscovite, biotite and phlogopite are common and widespread. Among others, calcite is very common and typical of calcium-rich rocks. Among aluminosilicates, kyanite, andalusite and sillimanite are typical metamorphic minerals of clay metamorphosed rocks. Sterolite, wollastonite, forsterite and cordierite are also typical metamorphic minerals in magnesia-rich rocks. To summarize the whole aspect which we have dealt here, physical properties of minerals are important and are useful in their identification, but its ultimate characteristic is its chemical composition. Bulk of the minerals that are building blocks of crustal rocks are composed from the most abundant 8 elements: oxygen, silicon, aluminum, iron, magnesium, calcium, sodium and potassium. Other elements only appear as guest artists. For convenience sake, minerals have unique chemical formula. Thus, as chemical symbols represent different elements, specific formulas represent each mineral. In fact, speak a lot about them. It could be as simple as gold for Au, or a bit more elaborate SiO2 for quartz or olivine, or far more complex as we found in the mineral glauconite. Classifying the large number of minerals brings order and method, and is based on its chemical composition, in particular the anionic group therein. Out of the 7 principal classes, silicates exhibit most diversity, comprises the bulk of Earth's crust. Quartz anoxide, yet studied along with silicates, is the most ubiquitous, making its home in igneous, sedimentary, metamorphic rocks as well as along with many ore deposits. However, many minerals have restricted occurrences: olivine in basic, ultrabasic rocks, gypsum in sedimentary rocks, garnet, kyanite in metamorphic rocks. A mental picture of chemical composition of minerals and their occurrences is the key towards a successful career in earth sciences. Hope you have learned something on this very important topic of classification of minerals and their chemical composition along with their broad occurrences. Thank you.